Our talk will evolve in that sense. First, we'll demonstrate what the on-prem OpenStack cloud is about. So we'll spend maybe a couple of minutes showing you what cloud we are running on and what services are needed to get this whole thing working. Then we'll spend a little bit of time on what our Kubernetes deployment on top of OpenStack looks like. From there, we'll move on to instructions on how to enable GPU usage and pass-through in OpenStack. For a lot of you guys who've done SRIOV kind of stuff, the instructions should look kind of familiar, but we'll go through that instructions. Then Nilima will spend a little bit of time talking about KubeFlow pipelines, a simple introduction of what problem they're trying to solve and what they're intended for. We have two demos coming up at the end. The first demo is basically an installation of Kubernetes and OpenStack. We show you how we do it and what are the intersection points there and what are the critical things to keep in mind. The final portion of the demo is going to show you an on-prem deployment of KubeFlow and porting some of the model and pipeline artifacts to Google Cloud and running it there. So that will culminate the entire demo. Finally, we'll point you to some references. We have a GitHub page where you can follow along some of the instructions that we have done here. Everything that we do here doesn't have any assumptions on what OpenStack cloud you're running on. We just use our OpenStack cloud as a case study. The only requirement, though, is you install Kubernetes on top of OpenStack. There are multiple ways to do this. We have one mechanism, but you're free to use whatever mechanism you have. So what are the requirements out of the on-prem OpenStack cloud to make this happen, right? So these requirements are nothing new. In terms of if any of you are running Kubernetes on top of OpenStack, some of these requirements will be known to you. We are using Cisco Vim, which is a Cisco Virtualized Infrastructure Manager. For people who don't know about it, we had this running in the booth. This is basically a NFV private cloud running OpenStack. Neutron LBAS integration is key because that's what we use to expose the Kubernetes services. So for instance, the Nginx controller, we expose the service using Neutron LBAS. We use Cinder for persistent storage. We don't actually care at the back end whether you're using Ceph, NetApp, SolidFire. For the purposes of this discussion, we are using Ceph as the back end, which means that we do read-write once with that. Compute nodes with GPU cards is basically one of the requirements. So we'll kind of talk a little bit about what you can do with an NVIDIA card and how do you enable GPU pass-through on your OpenStack compute nodes. You can actually do this even post-deployment. We do both. You can do this either on a tenant or provider network. If you use tenant network, just make sure you have enough floating IPs. What we suggest to try this out is at least have 3 compute nodes available so that, if you want to do some of this in production, you need to make sure that not all your Kubernetes masters land up on the same compute node. And if you have a compute node failure, you're going to have a problem. So one of the key things to build into your orchestration is things like anti-affinity to make sure that your Kubernetes workloads are more spread over. So with that, I'll move on to a little bit, just spend a minute talking about what our OpenStack cloud looks like. So it's a regular containerized OpenStack cloud. We are running OVS or VPP, either of it. For the purposes of this demonstration, we are running OVS as the network plugin. The virtual storage, we are using Ceph. We have also tried it on NetApp and SolidFire. It works fine, even in those environments. So this is a quick overview of what our OpenStack cloud and the architecture of the entire cloud that we are using. This is an on-prem, fully containerized OpenStack cloud, basically. So what do we do when we deploy Kubernetes on OpenStack? A lot of you, if you have used tools like KubeSpray and KubeADM, you will be aware of something called as a cloud provider. A cloud provider is essentially an interface in Kubernetes which allows you to specify information about the cloud, right? So in this particular case, Cisco Container Platform is a mechanism to deploy Kubernetes clusters and manage the lifecycle of those clusters on any cloud. It could be AWS, it could be Google Cloud, it could be OpenStack. So in this particular use case, we have used that platform to deploy Kubernetes on OpenStack. For the purposes of the discussions going forward, all we assume is that you use some platform to deploy Kubernetes on OpenStack. The key things to make sure here is we run a common CCP control plane. Essentially what that is Kubernetes orchestration as a service. So we run this in a unique OpenStack tenant. And after this service is up, it can deploy as many Kubernetes clusters on your cloud as you need and manage the lifecycle of the cloud. This interface will integrate with Cinder for persistent storage and Neutron LBAS for basically your load balancing and exposure of the Kubernetes service. So as you can see here, the CCP control plane will end up deploying tenant clusters. At the end of this, what happens is you have an OpenStack cloud on which, on one of the tenants in the OpenStack cloud, you have a fully deployed Kubernetes cluster. Now you have OpenStack, you have Kubernetes running. Now the next step is to basically, as you can see, this particular slide gives you a bit more picture of the control plane running in one of the tenants and the data plane running in a different tenant. At the end of the day, as you can see, there is integration with Cinder, and we use Calico as the network plugin. You could use Courier or anything of that sort as a plugin. Coming back to the critical pieces, the first step of getting all of this working is how do you get GPU pass-through working on OpenStack? That's the key thing, right? So we used NVIDIA GTX 1080 card. You could use any NVIDIA card. The instructions are not going to be vastly different, but the instructions here are for the NVIDIA card. There is a source that we used. It's a very good blog written by somebody, and it's pretty accurate. Those instructions were written for Rockies, but those instructions work for Queens as well. At a high level, our OpenStack deployment is Queens. What do you need to do at a high level? You need to enable GPU pass-through on the compute nodes. You need to make configuration changes on the OpenStack controller. You also need to make configuration changes on the OpenStack compute nodes. And you need to make some changes in your guest OS. In this particular case, the guest OS is going to be the nodes which are running your Kubernetes workers, basically. So the blog there details the instructions, but we'll talk a little bit about what you need to do on the compute host, right? So you need to load the appropriate modules for KVM and for PCI pass-through, basically. You need to have Intel IOMMU true. That is a kernel command line that you can make the changes in grub, and you basically reinitialize grub and reboot to make that change available. You need to blacklist some GPU modules so that those are passed through to the guest OS. These instructions, by the way, are documented on that blog link, so you can, they're step-by-step instructions by the author there. The controller config, if a lot of you are already doing SRIOV, you would be familiar with using PCI pass-through filters to the scheduler, so you don't need to do this extra step. But if you're not using SRIOV, make sure that you need to add the PCI pass-through filter to the scheduler filters. And configure the PCI alias with vendor and product ID. So basically, you can do LSPCI on a Linux host to get the information about what the vendor and product ID are, and plug those into the configs for these particular configs which you do on the controller and the compute node need to be done on nova.conf, Nova services. So you change nova.conf and restart the Nova services, you're good after that, basically. You also need to tag the flavor with the correct PCI alias that you just created in the step above. And after that, there is a known limitation with the NVIDIA KVM driver, so you need to add this metadata to the image. So you just use an OpenStack image set command to basically add this metadata to the image. Again, these instructions are clearly documented on the blog post that I shared before. Now in terms of, so you've gone ahead, you've configured what is needed on the OpenStack compute node, but to be able to use this, you also need to configure something on the guest OS. Two things need to be done. The first is you need to install the NVIDIA CUDA drivers on the compute node. This is done irrespective of whether you use Kubernetes or not. Let's say you're just running GPU workloads natively on a virtual machine, you need to install these drivers. Also, you need to install and enable the NVIDIA container runtime. That's a different Docker runtime that is needed for this to work. So the config changes for that are highlighted here. You need to change the daemon.json and basically add these configs. Finally, after you do all of this, you need to be able to give the information to the Kubernetes scheduler to be able to schedule on these GPU nodes. So for that, you need to install the NVIDIA device plugin. This is a daemon set which runs on all the nodes. And at this point of time, and it marks those nodes, so the Kubernetes scheduler will be able to actually schedule on these hosts at that point of time. So with that, I'm going to hand over to Nilima, who'll talk a little bit about the KubeFlow pipelines, and then we'll go on to the demos of how this whole thing comes together.
Thank you, Ajay. Hello, everyone. So KubeFlow is a project that started in 2017, basically with the intent of making it easy to run machine learning workloads on Kubernetes. So people started running different steps of KubeFlow, like getting data, collecting the data, cleaning up the data, pre-processing, training models and deploying models on top of KubeFlow. There was a problem that there was no easy way to collect all of these steps together and to reproduce each run that you conduct. So KubeFlow pipelines came about as an answer to that problem and was released late last year. It runs on top of vanilla Kubernetes. There are no requirements or restrictions. It doesn't really need even GPUs, though it can use GPUs if they're already present. So in our demo, we're going to be showing KubeFlow running on top of a Kubernetes cluster deployed by Cisco Container Platform, running on top of OpenStack, which Jay just talked about, and also run part of the pipeline on GKE on the public cloud. Cisco is one of the major contributors to KubeFlow. It's, in fact, the #2 contributor in terms of the code. Also, Cisco AI group is leading a lot of efforts on KubeFlow. One is named Katib, which is a hyperparameter search and auto machine learning model. And there are also contributions to KubeBench and PyTorch. This is a high-level architecture of KubeFlow pipelines. I'm not sure if it's very visible. The top box that you see here is the main component, which is the pipeline API server. It takes the job of looking at your KubeFlow pipeline that you have defined and running each of the stages of the pipeline as jobs on your Kubernetes cluster. The KubeFlow pipelines uses two databases. One is a MySQL server in which it stores metadata information. So you create a pipeline, the metadata information about the pipeline, how many experiments correspond to that pipeline, what runs were done in the past for using that pipeline, and what are the parameters used for each run. So if you come up with a model or an accuracy today, somebody will be able to reproduce it exactly after a month on a completely different setup once they have this information. So all of that metadata is stored in a MySQL database. KubeFlow also provides Minio database, Minio server, which allows you to store artifacts. So if you're building a model and you want to hand off that model to the next stage of your pipeline, you don't necessarily need to have shared storage. You can just use the KubeFlow pipelines and store it as an artifact that you hand over to the next stage. So there are also a lot of other components that you can see here. One of the main things is the Argo workflow controller. So KubeFlow uses Argo to orchestrate the different pipeline stages. And they can be run in parallel. You can provide the dependency graph between different stages, and they're handed over to the Argo workflow controller. KubeFlow is also packaged by default with a variety of visualization tools like TensorBoard, and also a Jupyter Hub controller, which allows you to run Jupyter notebooks and create pipelines, run workloads, and develop interactively. So you don't have to build everything offline using a CLI and upload it. You can do that, but you can also do interactive development using Jupyter notebooks. So with that, we will start the demo. Ajay will first do the demo of setting up the CCP cluster on top of OpenStack, and then I'll do the demo of installing KubeFlow and running a KubeFlow workload on-prem and in the public cloud.
Thanks, Nilima.
Yeah.
So like Nilima spoke, basically one of the requirements for KubeFlow to in fact run is you need a Kubernetes cluster on top of OpenStack. So the first portion of the demo will show you how we deploy a Kubernetes cluster on top of OpenStack, and then Nilima will basically show you at that point the KubeFlow pipeline installation on top of Kubernetes at that point of time. So here basically we have an orchestration node for our OpenStack installation. And at this point of time, we basically, what I'm showing here is the Kubernetes installation itself is a KubeFlo image. This is the image for the Kubernetes tenant cluster. So this is the input file for our deployment. So as you can see, you give it information about what your OpenStack external network is, what is the path to your DNS server, and so on and so forth. And what this will do at the end of it is either on a tenant OpenStack network or on a provider OpenStack network, it will go ahead and deploy the Cisco control plane for Kubernetes, and it will actually deploy Kubernetes tenant clusters. So we'll go ahead and at this point of time fire off the deployment of Kubernetes on top of OpenStack. So as you can see, there's commands to basically install the Cisco container platform and also to install multiple tenant clusters on top of it. So when we fire off, the first thing it does is it creates a common tenant inside of OpenStack and deploys all the resources of the Cisco container platform control plane on top of it. This control plane is essentially an API endpoint to which you can talk to create a large number of 1 to n Kubernetes clusters and basically manage the lifecycle of the Kubernetes cluster. What this control plane is capable of doing after it's been installed is not only can it deploy your Kubernetes clusters for you, it can also manage the lifecycle of those clusters, and it can actually auto-heal from problems. Like let's say your compute node in OpenStack goes down and you lose one of the workers, it can automatically spawn another VM on a different worker and basically continue from there. So here I'm logging on to the OpenStack dashboard at this point of time and showing you that the deployment of the control plane of Cisco Container Platform has started. So this will basically go ahead, deploy a bootstrap VM, and will ultimately stand up an entire control plane, which is essentially Kubernetes orchestration as a service on top of OpenStack. So here we are talking to the REST API of this endpoint to basically create this cluster and expose. As you can see, it is using Neutron, LBAS, and Nginx controller to actually expose the entire control plane through a UI. So at that point of time, you should be able to create any number of Kubernetes clusters talking to this API endpoint or by using the UI dashboard that will just pop up after this. So here the control plane installation is successful. This means that at this point of time, I can go ahead and create any number of Kubernetes clusters on top of this OpenStack cloud. So I'm going to log in and show you here. You can see it's already created a Kubernetes cluster. This is the control plane of this CCP platform is also itself a Kubernetes cluster. So as you can see, it's got 3 master and 3 worker nodes. And here we are actually showing you the UI where you can log in and create multiple tenant clusters. So at this point, once the control plane is created, the next step is to actually create a tenant cluster. The objective of creating the tenant cluster is now we have a cluster that we need to get ready so that Nilima can actually go ahead and deploy the KubeFlow pipeline on top of that cluster. So here it's going to go ahead, deploy the tenant cluster, and at the end of this command, you will get a fully running Kubernetes cluster on top of OpenStack with exposure of the Kube API endpoints through Neutron LBAS and persistent storage through Cinder at this point of time. Here, this tenant cluster deployment is done, and you can actually manage this tenant cluster through a user interface that we provide if you need to. So here, I'm just going to log into the tenant cluster, and here you'll actually see that it would have deployed the CCP control plane. And one of the things that this control plane does is, remember I showed you instructions on the configuration that you need to do for the NVIDIA drivers on the guest OS. It automatically does this as part of the installation of the worker nodes. So that's pre-done for you. So you basically don't need to do any of that going forward. So at this point of time, the Cisco Container Platform has successfully deployed Kubernetes and Kubernetes clusters, and you can basically manage the lifecycle of those clusters through the UI if you need to. So at this point of time, given that Kubernetes has been deployed on OpenStack, GPU pass-through on the compute node is basically working, we are now ready to deploy the KubeFlow pipeline on top of it and get everything working end-to-end. So with that, I'll hand over to Nilima, who will take on the next demo.
So first, we'll start with KubeFlow installation on the OpenStack cluster. The identical steps were followed for GCP cluster, which we'll see later on. The first step is to install the KubeFlow installer, which is called KFCTL. And the second step is to install a Python DSL compiler, which compiles the specification of your KubeFlow pipelines and runs them. So these 2 steps can be done on your development machine or wherever you want to develop your pipeline components. All they need is a kubeconfig, which points to the Kubernetes cluster on which they can create and launch the workloads. So we've installed KFCTL and the DSL compiler. Now let's initialize a KubeFlow application. So I'm not doing anything specific to pipelines at the moment. This is a plain KubeFlow application initialization because As of KubeFlow version 0.13, KubeFlow pipelines is a core component. So once you install KubeFlow, pipelines is automatically started. So we initialize it, kfctl init creates a dummy a skeleton project and generates YAML files, components for KubeFlow. Kfctl apply basically applies these components into your Kubernetes cluster. So at this point, you can use your standard Kubernetes commands like get pods, get workflows, which is CRD that is installed by KubeFlow pipeline. So all of those you can get using the standard kubectl command. Okay, and then KubeFlow is exposed, KubeFlow services are exposed using an ambassador ingress. So this is where I'm basically going to the ambassador ingress, and this is the KubeFlow central dashboard, which gives you a central place to look at all the services provided by KubeFlow, one of which is the pipeline dashboard, as you can see here. For the demo today, we're going to launch 2 notebooks. So the first one is GPU notebook, and the second one is CPU notebook. So if you can see the first one that says demo, it's actually using only CPUs, and the pipeline demo is actually using a GPU notebook from Jupyter Hub. So we start a Jupyter notebook, and we first do the first step of the demo, which is building a model. Right, so this is a pipeline. Each pipeline is run as, each iteration of a pipeline running instance is called a run, and a combination of the runs is called an experiment. So to be able to start a KubeFlow pipeline, you have to create an experiment. So that's the first step we do here. We're creating an experiment in which all the runs which have the parameter specific to your iterations will be stored. Next step is we define the pipeline graph. So basically, if you take away one thing from this talk, like what is a pipeline? This is a pipeline, right? Each of the steps in a pipeline is what we call a containerized operation. So it runs inside a container, inside a Kubernetes pod. You can develop them, you can use Docker build or any mechanism that you like to package these containers, and then give the requirements, whatever they have, like arguments to start your container here. Right, this is almost equivalent to how you would give a pod YAML spec. But you could also use KubeFlow pipeline built-in function called function to container op, which takes any Python code, builds a container image, and then runs it as a pipeline component. So at the end of the day, what we are doing is running pipeline components, basically, as containers. So we define multiple steps here: downloading the data, pre-processing, training, starting TensorBoard prediction, and creating a confusion matrix just for visualization. And then we define a shared storage here. So as I talked about, we have artifacts. You can use artifacts which can communicate data across different stages. But here I'm downloading a large amount of image data, and I'm actually sharing it across multiple stages. So I have a shared NFS server because, as Ajay mentioned, Cinder provides a read-write once storage, and it can't be attached to multiple pieces, multiple stages of the pipeline, multiple pods at the same time. So we start an NFS server to be able to handle that. And then here we define the pipeline graph. So here we're saying, okay, first do a download, then you do pre-processing, then you do training, and so on. So once you define the pipeline, the next step is to create a pipeline tar bundle using the DSL compiler. So that's a compile step. And then you run your experiment. So once you start a run, you can see from the pipeline dashboard UI what is happening at each stage. This example we have here is image classification, which is using transfer learning. So it takes the MobileNet feature set to start with and builds on top of it to classify bolts. Oh, okay. So that was in our slides, and we missed the slides before we came to the demo. So here it's doing the pre-processing step where it's building the bottleneck cache. So it basically pre-processes images. In the transfer learning step, the first step is to take each image and to generate a feature vector out of that image, and that is going to be reused multiple times in your training step. So you don't want to each time recreate the feature vector. So what we do here is separate out the pre-processing step, build a cache, and then run the training step where we are training the data, the final data classification information. So you can see pretty quickly the accuracy goes up. And once the model is trained and ready, we can then take it and serve it using TensorFlow serving. So if you remember, the graph that we defined actually said that, okay, after training is done, you can do deploy, TensorBoard, and predict steps in parallel. So KubeFlow pipeline starts off 3 different tasks in parallel, and you can see them here. It starts a TensorBoard UI where you can visualize. It starts a confusion matrix UI where we can look at the accuracy of this prediction. And the deploy step is starting a TensorFlow serving job, which gives a Kubernetes service that we will connect to when we are trying to run inference after this. So it takes a minute for the deploy step to start the TensorFlow serving, the end of which we get the service here. So as you can see, it says Open Infra Summit Bolt Trainer. So this service is what we're going to be talking to in the next stage, where we run a client application to do Bolt image classification. So
if you want, you can switch back and show the slide if you need.
That's okay. So after we finish. So this is the, so now we're going to start the client application, which is going to consume the model that we trained. All of this is still running on-prem. We haven't gone to public cloud yet. So we take the service IP from here, put it into the server information. So this is the only thing that changes based on where you're running. Where is this service available and how do you reach it, right? So here I'm running on-prem and I give the service name inside this cluster. And basically all it does is sends a prediction request to the TensorFlow serving job that you have running there. So the code defined, and we'll now ask it to classify 2 different images. That's the service endpoint as we talked about. So this is the first one. So before doing the demo, I was actually trying it out on a smaller training example. So the accuracy there was horrible. And for the second image, it basically says bad, right? But then once you basically, once we have finished the training and the model that is serving now, you run classification using that model, we get pretty high accuracy at this point. So we have done training, serving, inference, and we can look at the built-in visualizations that you have. This is the standard TensorBoard dashboard, which is showing us the accuracy and cross entropy. As you see, the accuracy goes up and the cross entropy goes down with the number of steps that increase. I've run this with 2,000 steps. And you can see the built-in visualization for the confusion matrix as well. All right, so we've completed the pipeline installation and deployment of the pipeline on-prem. Now we're going to do the same thing on GKE, except we're not going to do the complete pipeline. Right. So this is a GKE cluster. We have pre-created the GKE cluster. We don't walk through the steps of creation again. And then we've installed KubeFlow. So you can see it in your services. It basically shows up as a load balancer. We go to the Jupyter notebook that is running on this load balancer IP. So everything is same. It looks identical, except for the IP, nothing changes. So you don't even need to know that it is running on a different cloud, right? So we do the same image serving, model serving here. We don't train the model again because we've already done it. We've transferred the model from the on-prem training to the public cloud using Google storage buckets. That's one step which is manual today. Well, we could push it and then you pull it, but there still needs to be some kind of shared storage through which we are communicating that model information, right? So now the model is downloaded and now we're ready to serve. So run the KubeFlow pipeline with one step. All it does is serves the model. And we do the same thing, wait for the trainer to be ready, take the service name or IP of the service that is running, which is doing the TensorFlow serving, and then go back and do the same inference as we did in our on-prem cluster. So it's doing the same thing here. So just the only thing that changes is the service endpoint. We try to classify. Again, we get pretty good accuracy because it's the same model. It should be identical here. Both the images come out to be pretty much the same. Right. So this is the end of the demo. We'll go back to the slides. closed? Okay. Okay. Right. So before we started the demo, we actually wanted to show you the topology of how it looked as on the OpenStack cluster. So you can actually see we use floating IP to be able to access the Kubernetes API server. So this is a CCP control plane, and this is a tenant cluster. And then this is a summary of the example that we saw today. So it's basically doing a classification of bolts into different types, which is supposedly a very important task if you're on the machine the floor, where you're trying to select a specific bolt to put into a specific workflow. If you pick the wrong bolt, you could potentially ruin your very costly machine. So it's a very important task that needs to be done. So we're basically making it easy, because we take the human out of the picture and put the machine in and say, okay, classify for me and tell me the right thing. And we've shown, we've run this on CVIM, which is the on-prem OpenStack deployment, and on public cloud. All right, as a summary, basically, we talked about and talked through the steps of integrating GPU on OpenStack, basically pass-through mode of GPU for machine learning applications. We've talked about how to deploy a KubeFlow pipeline on top of Kubernetes and share this pipeline across different frameworks. So basically, we took the pipeline that we built on-prem, put it on the public cloud. Identically, you can run it. We talked about how you can transfer pipelines across different clusters. We talked about how you can transfer artifacts not so seamlessly across different clusters, because if you're in the same cluster, you can use Minio and reuse the artifacts. But if you're actually on two different separated clusters which don't have network connectivity, then you need to have some common shared storage where you push your model and consume it. This is a lot of help from our Cisco AI team, which is the contributor to KubeFlow, in getting the demo working and hardware and everything. We've created a GitHub link, the last link here, where we've documented the entire process that we've followed and given links to a reference application as well that you can run to get started with KubeFlow pipelines. It's pretty straightforward. The only gotcha that we saw with running it on-prem versus running it in the public cloud is the assumption that most of the things in KubeFlow pipeline are built for GCP. Like, they assume there's a shared storage which is read-write many, which is not a given if you're running on-prem on an OpenStack cloud without you could have something that's a hyperconverged storage in the middle, but assuming you don't have it and you have only Cinder, then you need some kind of a solution to get it working. So there were small issues like that. Like, if you have two storage classes and your storage class doesn't have any annotations, the Jupyter notebook doesn't start, so stuff like that. But basically, the steps that we followed are documented here, and you should be able to follow them along. That's it from us. Thank you. Any questions? Yeah, please go to the.
Can you talk into the mic?
All right, thank you for your presentation. Yeah, I was wondering if just a question about running machine learning on top of on virtualization with a virtualization layer. I was wondering if you did some benchmark and if you knew if there were a lot of overhead running on a virtualized environment versus bare metal.
So we've not directly compared identical environments on bare metal to a virtualized platform, but the one test that we did was to see how NVLink performs on a virtualized environment using Passthrough. And we found that it pretty much scaled linearly, so we didn't really see any performance overhead. We did not have an identical test bed to actually test it across bare metal and OpenStack or VMware. Yeah.
Thanks. Second, just quick question, might be a tiny bit off topic though, just regarding pass-through security issues. As a public cloud provider who wants to provide GPU to my customers in their VMs, how GPU pass-through obviously has some strong security issues. It's basically giving the full control of the GPU card to the end user, to the customer, and he can do pretty much everything with it. Do you know how to solve this kind of issues? Did you had a look at this?
So actually, that's a good question, because if you compare that with SRIOV, for instance, there has been work in Neutron to actually do things like trust mode and that kind of stuff. But unfortunately, what we have found is on the GPU bucket, I don't think we are there yet, because GPU integration itself in OpenStack is pretty new. It's not something which has matured in that context. So while we found that some of the security features are more advanced on the SRIOV side, no, that concern remains at this point of time.
Thank you.
Any more questions? Actually, the steps are all documented in that GitHub site, so we haven't made any assumptions about which cloud you're running on and all that stuff. So if you want to try this out on your OpenStack deployment, the only thing that you need to do is install Kubernetes. You can use KubeSpray or anything of that sort for doing that, and then you should be able to follow along these instructions.
All right, thank you.
Thanks a lot for coming.